In this video, we'll look at inverse trig functions. So there are two things that we need to remember from when we defined inverse functions. The first is what the condition was for if there even were inverse functions. And so to check that, what we needed to know was if the function that you were dealing with is one-to-one. So inverses exist if the function is 1 to 1. Now, graphically, we tested whether or not a function was 1 to 1 using the horizontal line test. Okay, so our goal is to define inverse functions for the trig functions. And in this video, we'll just do it for sine and cosine. So if, for example, we think about sine, I'll just draw a quick and dirty graph here for what sine looks like. It's something like this, and then it repeats over and over again, right? Okay, so there's something like that. Then we have a bit of a problem because not only does this function fail the horizontal line test, it really fails it. So there I've drawn in a sample horizontal line, and notice that the function, the graph of it, intersects that horizontal line not just a couple times, but in fact infinitely many times. Okay, so what that means is that sine x doesn't have an inverse. Okay, but what it does have is a sort of inverse. And the way that we're going to get around doing this is by using the fact that sine is a periodic function. So if you look at the graph of this, you could say, well, the point here where it crosses, and the point here where it crosses, and so on, all of this is like this point here and this point over there, well, they're kind of the same thing. And similarly, this one is similar to that one, and so on. So you could say, well, why don't we just restrict our attention to one of these little, one period? And that doesn't even work because, so if I just sketch this for one period, then everything is okay with this one except the x-axis. Actually, no, sorry, all of them fail. The only points that are good are the one here at the tip top and the one at the very bottom. So what we have to do is restrict our attention to even smaller of a piece of the graph. And with sine, the typical way that we do it, actually let me do sine of x, is to only look at quadrants 1 and 4. And the reason for this is that in quadrant 1, sine is positive, and in quadrant 4 it's negative. So let me draw the graph of this function, and this will go between the biggest that we'll deal with is pi halves, and then we'll, on the negative end, be down at negative pi halves. And so the quadrant 1 stuff are the angles in between 0 and pi halves, and then the stuff that's in quadrant 4, I'm going to choose here to represent that as stuff between negative pi halves and 0, so that's that stuff there. Okay, and if I graph the sine function here, then what I get is something like this. Okay, so this is just a little small part of the wavy pattern. So on my big graph over here, what I've drawn is essentially just the part that I've highlighted in light blue there. So the light blue here and the dark blue over here, those are really the same thing. And if you notice in this, the graph actually does pass the horizontal line test. Okay, so this restriction of sine, okay, so we have restricted the domain of sine of x. And now that we've done so, it has an inverse. And the name for this inverse, there's actually two ways to write it, is sine inverse. Okay, but I don't particularly care for that way of writing it. Oops, not arc cos, arc sine. I kind of prefer to write it arc sine of x. The reason I don't like sine to the minus 1 is that you're tempted to think that this means it's 1 over sine x, and that's not true. And arc sine sort of gets around that ambiguity. Okay, so by restricting the domain of the function, we've made it so that there was an inverse. Okay, so let's look at a quick example problem. Let's say that we were asked to figure out what arc sine of 0 is. So what this function means, so let's say that arc sine of 0 is a number that we're trying to look for. So let's just call it y for some unknown answer. Then this means that if you take sine of y, you need to get 0, and because of the restriction that we put on our domain, it needs to be the case that y is in between pi halves negative and pi halves positive. Okay, and the reason that for that is because what we're looking for is an angle in between negative pi halves and pi halves, because that's what the domain of the blue graph was. Okay, so if you just ask when is sine y equal to 0, there are actually infinitely many answers to that, but there's only one of them that lives in between negative pi halves and pi halves. And if you think about it for a little while, then you realize that y equals 0 is the only such answer. Now, how did I know y equals 0 does this? Essentially what I'm doing is thinking backwards. Because I've memorized the unit circle, I know that sine of 0 is 0. And so if somebody asks me what's an angle that makes sine equal to 0, I just sort of think through the unit circle backwards to figure out what an angle might be. And then because there are lots of answers, this condition here tells me which one of them I need to pick out. Okay, so in the next slide, we'll look at a similar example of this for cosine. Okay, so next let's look at basically the same idea but with cosine instead. So the graph of cosine, I'll just sketch it here for reference sake, has the same problem that the sine graph does, namely it also gloriously fails the horizontal line test. But we can basically pull the same trick. And the trick will be slightly different here, because if you notice, so right there is negative pi halves and right there is pi halves. I don't want to pick quadrants 1 and 4 because cosine's actually positive in both of them. So what I'm going to do instead is restrict my attention to this piece here, and I'll highlight that in dark blue. I'm going to look at this part of the graph. So that ranges between 0 and, on the far end, pi. Okay, so let me just sort of redraw that graph, just that little piece of it. So cosine starts up at 1, and it's going to end at minus 1. At pi halves it's 0, and then it's sort of the curvy shape in between. Okay, so this segment does pass the horizontal line test, but I've restricted myself so that the x's had to this time be between 0 and pi, i.e. quadrants 1 and 2. So in quadrant 1, the function was positive, and in quadrant 2, it was negative, and all the y values that the function ever hits are represented just on these two quadrants. On quadrants 3 and 4, that would be the part, and I'll graph this in pink, quadrants 3 and 4 would be this part of the graph, and you notice that essentially it's the same thing as the blue part, it's just sort of flipped backwards. So all I really need here is just this little piece. Okay, so let's take a computation with cosine. So let's suppose that I'm asked, what's the arc cosine of 1/2? Okay, so let me call this an answer. Answer, I have no idea what it is, so I'll call it y. And arc cosine equals y means that cosine of y equals 1/2, and that the y needs to be between 0 and pi. Okay, so similar to the sine case, the only difference between these two is that for cosine we demand that the angle live in quadrants 1 or 2, not in quadrants 1 or 4 like with sine. Okay, so again, I'm going to basically just use the unit circle in reverse. So I think about it for a minute and I say, well, I do know that cosine of pi thirds does equal 1/2, and pi thirds also happens to be inside that interval, and so those two things together tell me that the angle here needs to be pi thirds. Okay, so the thing that's different here between this and previous times we've used inverse functions, this sort of back and forth thing that we did in this step here and this step here might kind of remind you of a similar sort of situation. So we've previously used this sort of backwards forwards view when we did stuff like this. We said that y equals a to the x was equivalent to saying that x was the log base a of y. Okay, so we were able to convert between a statement in exponential form and a statement in logarithmic form by knowing that the logarithm and the exponential function were inverse functions of each other. And essentially we're doing that same thing here with the trig functions. But the one extra wrinkle is that we have to restrict the domain of the trig functions, or else we can't even do this sort of thing. Okay, so in class we'll look at how we do this with the other 4 trig functions and some more complicated examples.